Question 3 is a question on equilibria, equilibrium constants, Kc, and you're given a typical equilibrium, hydrogen, iodine and 2HI in equilibrium with each other, and you were given the delta H for the forward reaction is minus 9 kilojoules per mole, so that's exothermic. Sorry about that, that's just my method for calculating Kc. It's called the ICE method. I'll explain why if you haven't seen the video. So we're told that there are 2 moles of hydrogen, 2 times 10 to the minus 3 moles of hydrogen and 4 times 10 to the minus 3 moles of iodine in a 1 decimeter cube container. That's quite nice of them because the concentrations are nice and easy to calculate when it's 1 decimeter cubed because the moles are the concentrations. So chemist seals a container, mixture is heated and left to reach equilibrium. At equilibrium we're told we've got 3 times 10 to the minus 4 moles of hydrogen. Calculate Kc, include the units if any. And we must give our answer to 3 significant figures. Okay, so here's my way of doing these. If you've watched the videos you'll know exactly what I'm doing here. So there's the equilibrium. And we were told there were 2 times 10 to the minus 3 moles of this, 4 times 10 to the minus 3 moles of this. So at the very start there wouldn't be any of those. So the I stands for initial moles. I'm going to jump down to E now. This stands for equilibrium moles. So we were told that at equilibrium there were 3 times 10 to the minus 4 moles of hydrogen. So that means that there's been a change of that down to that, and so therefore the change is a drop minus 0.0017. I'll just explain where that comes from. So we're going from, that's our starting moles, initial, and they're our equilibrium moles, so the hydrogen's dropped by this amount. So this C stands for change. So once we know this change here, we can feed that into the rest of the equilibrium. So we knew the initial moles of iodine were that. The change is going to be the same because this is a 1-to-1 ratio. So that'll go from that to that, 2.3 times 10 to the minus 3. The change in the HI, we've got to factor in the mole ratio here. So that's a 1-to-2 ratio. So we're going to get twice as many moles of these produced. So that's an increase plus 0.0017 times 2. So that's going to mean that at equilibrium we'll have this many moles of HI. We would then write our expression for Kc. So it's the concentration of the products squared over the concentration of the reactants. Because the volume of the container was 1 decimeter cubed, these moles are effectively concentrations. If the volume was not 1, you'd need to divide these by the volume in decimeters cubed to get them into concentrations, but we don't need to do that here. So we feed these numbers in, and to 3 significant figures, there's your answer. And the units, well, there aren't any units, so you can write none or no units. Don't just leave a blank or a dash or something. You need to say to the examiner, I know that there are no units. How did we work that out? We've got moles per decimeter cubed squared on the top and moles per decimeter cubed squared on the bottom. So we've got to fill in a table now. The chemist uses 3 times 10 to the minus 3 moles of hydrogen instead of 2 times 10 to the minus 3. So that's obviously an increase, more moles of hydrogen. So the moles of hydrogen at equilibrium would be greater. The iodine would be smaller because they're going to need to react with those extra moles of hydrogen, so that would be smaller. And the upshot of that would be you'd have more moles of HI because to minimise the change, the Le Chatelier's principle, if you like. The extra H2 will react with the I2 and therefore produce more HI as a result. Chemist heats the mixture to a higher temperature at constant pressure. Explain whether the value of Kc would be greater, smaller or the same. Well, temperature does alter Kc, so it will change. Let's have a look back at the equilibrium. So we know the forward reaction is exothermic. So if we increase the temperature, that's going to favour the reverse endothermic reaction, and that means we're going to have more of these and less of this, and so therefore Kc would drop because the equilibrium is shifting to the left. So forward reaction is exothermic. Higher temperatures favour the endothermic reaction, which in this case is the reverse reaction. Equilibrium shifts backwards, therefore Kc decreases. Remember, Kc is a measure of how much the reaction's going in the forwards direction. And then the final bit, the chemist increases the pressure, and so therefore the value of Kc doesn't change because Kc is only temperature dependent. So Kc stays the same. Kc is not altered by changes in pressure. It's only affected by the temperature.